May I have your attention, please? We are about to start with the second plenary of the annual meeting of the European Astronomical Society. So what we have today first is a presentation of an award and the subsequent talk. So I'm very honored to present the award, the Jocelyn Bell Burnell Inspirational Medal in 2025, to the archive for its impact on astrophysical research, thanks to open, free, and worldwide distribution of scientific articles. I would like to welcome on stage Licia Verde and Ralph Weyers to accept their award. Now, please, you're welcome to continue with your talk.
So, first of all, on behalf of the staff and all the volunteers at Archive, it is an honor and we are humbled to actually be recognized by this award. Thank you, EAS, and thank you to the whole community behind it. You are the big part of the submitter, reader, and writer of the archive. So let's start with a little bit of history and see where Archive got, where it got. And the way to summarize that is a rebel movement that has gone mainstream. So let's reflect a little bit on the role of preprint and the pace of science. Some of you will probably remember when preprint happened before the internet. And the scholarly journal, in order to, from when they receive a paper, go through the entire peer review system, editing system, and distribution system, until it went to the institutional libraries, was taking months, if not years. Today, the distribution to the library, the actual printout, it's cut out, it still gets distributed electronically, but it still takes months. Pre-internet, the preprints were actually preprint, they were printed and mailed to few privileged institutions, and the time of months to almost years were cut out to weeks to months. But preprint now get distributed to everyone through the internet with a time scale of hours or weekend and holidays days. So before 1989, preprints were actually draft paper that the author shared with colleagues manually or on paper and were mailed out. In 1989, Joan Kohn realized that tech had flexibility, and the small size of the file would allow the preprint to be shared by email through a list of researchers that was manually curated by her. Then the internet happened, and Paul Ginsberg realized of the potential of the internet in this distribution and automatized the distribution list, making the first internet-based distribution of preprint, and that was the beginning of the archive. And there you have an actual picture of the actual computer sitting on Paul's desk that was serving the archive. In 1994, Archive started using the World Wide Web and became a website. And then the rest is history in the sense that come the 2010, also other preprint, electronic preprint started. The first one was bioRxiv, extended to the biosciences and so on. So now Archive hosts preprint, also conference proceeding, and publish article, the author-accepted version of the manuscript. So here you see the first version of the web-based version of the archive. Started with physics in 1991, math follow in 92, computer science in 93, although computer science really took off around 2015, and other subjects later on. This is a sketch from Los Alamos Science in an article in 1994, which actually really represent what the nature and the spirit of archive was. You can see Paul biking, he likes to bike, and running his computer, you saw it in the previous picture, and spinning all this knowledge and papers on the World Wide Web. Archive remained at Los Alamos until 2001, where it moved to Cornell, and it has stayed under the Cornell umbrella to this day. And the rest is history. BioArchive, MedArchive, we've heard about Zenodo by CERN, supported by CERN, and even in the humanities, the Philosophy of Science Archive. Current status of archive, if you are here, probably you know what I mean. The day in the life of researchers in physics, astronomy, mathematics, computer science is wake up, get coffee, check archive. And then when you go to work in a university or research center, many of us have coffee and journal club. That's a picture from my own research group where one discusses papers in the archive. So the key is facts, accessible, global, moderated, and curated, and findable repository. You all know how the circle goes. The author submits the research. There is the moderator in archive do some quality assurance check and check the submission. A full PDF is produced, and the listing is produced. And then they are emailed out or released on the web in a time scale of hours, and then researcher the next day discovers new papers, new idea, and the circle continue by fomenting new research idea and new publication. So if you want to be precise and use more technical term, archive cover article submission, although it's preprint or e-print, compilation, production, retrieval, search and discovery, web distribution for human reader, API for access for machine, content curation, and preservation. You don't think twice, you think I put the paper in the archive, even if my hard disk crashes, it will still be there. There is one key step in all this process, which is moderation. And here, the balance is to being fast versus being accurate. Archive is lightly fast, but it cannot be as accurate as a peer review. So for archive, speed is of essence, and we can have a discussion of what the role of peer review is. We know peer review does not ensure correctness, but the bar for the archive moderation is different from the bar from a journal. But the moderation is a very important step of the process. So the team vets submission for quality assurance, copyright, technical health, overlap, that's not plagiarism, is overlap, classification and professional standard. Sometimes submissions are put on hold or are declined, and there are all a set of reasons, and that's all described on the archive webpage. The overall rejection rate is 4%, although it varies across categories. Now, of course, this will be much higher if it wasn't moderated as well and uniformly, because people know that they will submit to archive something of a certain quality, otherwise it will not go through. So it's a quick superficial vetting. It's not referee, and that's very important because the team resources that you need to compensate and equalize the kind of quality you want on the product. And the key is that it relies on work by 218 moderator and 7 staff members. That's a lot of people working for archive for free, and that's what makes the community Probably many of you are in the audience, so thank you. And I now stop here and I let Ralph continue. Ralph is the chair of the editorial committee, so he knows the in and outs of moderation. Thank you.
And of course, Licia is chair of the Science Advisory Committee, which makes it interesting that since 5% of the papers on arXiv are in astronomy, but 2 of the chairs of the 3 advisory boards are astronomers, you can ask yourself a question about the activity that astronomers have towards arXiv. So if you look at arXiv today, we have had more than 3 billion downloads. There are 5 million active users every month in arXiv. We had 250,000 new submissions in 2024. We are threatening very quickly to go over the 300,000 in this year because we got 25,000 already in May. And we have about 300 members who help us support arXiv. As Licia said, we have 218 moderators, which is too few for the 150 categories we have. So increasing and making more robust our moderator pool is a goal over the coming years. And then there are the advisory council members. And in total, there are 24 staff. That includes not only those who make sure the moderation works, but also making sure that the technical side works, making sure that the hardware is always in order, that the software is kept up to date, and so on. So arXiv is supported by members, by affiliates, by sponsors. For example, Cornell, which now hosts arXiv, still pays about 40% of the budget. And all the rest is in majority paid for by members. You know, many universities that publish in arXiv submit a small amount of money, and that altogether is not negligible, but for example, the Simons Foundation pays a quarter of the rest. So charitable foundations are very important. arXiv is governed by Cornell Tech, which is the arXiv steward, and it has a faculty director and associate director, and then it has 3 sections on software, operations, and science. And it has 3 advisory councils to keep it all organized and running well. And here you see our faculty director, Ramin Zabi. He's a computer scientist, and he also has an association with Google, so he knows all about data systems. And the third important astronomer is the middle one of those, Stein Sigurdsson, who is originally Icelandic, but also American, and who is the science director of arXiv, and he is a professor of astrophysics at Penn State. Right, this is the team. So these are the people who every day make sure that your papers get processed and that the papers that are processed arrive in your mailbox or in your favorite arXiv viewing website. And it's now centered in New York City on Roosevelt Island, where Cornell Tech is. Now, what will happen next? What does arXiv need to do to remain viable? Well, first of all, we need quite a bit of computer innovation. arXiv at its core still runs Perl scripts that are 30 years old. And so our first job is to make that better. We want arXiv to be robust, reliable, and responsible. We don't want single points of failure, and we want it to be globally supported and globally represented. And the current state and funded plans are that the part of storing and serving papers is already done in the cloud. That part of the software has been innovated, and you may have noticed that over the past year or so, that became a lot faster and a lot more robust. In 2 steps, one finishing this fall, the other one finishing next spring, we will innovate the entire software, including the submission software, so that that also becomes more robust. And what we also want to do is to expand the moderation time. So your paper will be delayed by about 24 extra hours to make sure that the community of arXiv can truly become global. At the moment, the moderation base is still mostly US and European based, because it's very hard for people in Asia to do that in the middle of the night. And of course, we want to change that. So we want to make that delay a little bit longer so that everybody, no matter where they are in the world, can do their moderation work during normal hours. And the future hope is, of course, that we will also be more supported by those other continents. At the moment, 90% of the funding comes from the US. And we want more of the moderators and board members, but also more of the support to come from outside the US, again, to make it more robust and to make it also innovation capable. At the moment, the software innovation is done by a single grant from the Simons Foundation and the Zuckerberg Foundation. And the normal money of archive is just enough to keep it minimally going. Right, as I noted on one of the earlier slides, at the moment, we receive 250,000 papers a year and we use $2 million a year. So processing an archive paper and then forever serving it up costs $8. Think about that. We think about double is needed to do it innovatively and good. Now, we also want to innovate the organization because, again, currently the vast majority of funding comes from the US. The governance is by Cornell. The volunteer force is largely US and European. We want to globalize that. We want to serve the world and we want to be governed and funded by the world. That means we want to make archive more broadly supported and governed. For example, to house it not strictly at Cornell, but make it governed by a US foundation. That's one of the models we are thinking about right now. And to create a board that represents all the supporting organizations in the whole world. And of course, our hopes, but also our question is then, how can we make other important users of archive, specifically let's think about Europe, because that's where we are, contribute a larger fraction of that what is needed to make archive run, both in person power and in money. And how do we become a stronger partner in our archive, also in actively thinking about what archive should be doing? So, could there be something like archive.eu, a parallel organization to the American one, that doesn't try to run its own archive, but that works in team with the American part and maybe also with an Asian part, so that there are multiple supporters of archive, so that in difficult political situations, and I don't have to say much more, one could afford to lose a supporting organization and still keep archive going, right? One never knows. We've learned in recent times that not everything is as self-evident as maybe one day we thought. So come and see us at the archive booth or come and talk to us in the hallways if you have ideas about this, if you want to know more about this. We are here. And the important thing is archive is open above all, and archive is for scientists, by scientists, and of scientists. So thank you very much, again, on behalf of all of us.
So, thank you very much to both Licia and Ralph for this inspirational presentation. And are there any questions to them? Yes.
Thank you. So first of all, and I think I speak on more than just my behalf, thank you for everything that you're doing. Yes. Now, I actually have a request, but I'm going to disguise it as a question. And I hope it's not too controversial, but when making the daily list of papers, is there a reason not to randomize the order?
There is... archive is governed by some old traditions, so there is the 2 p.m. Eastern time race. That will end as soon as the new software is in place. The list will become random by timing.
Thank you.
Right, so we now have large language models that can essentially produce text at very rapid speeds. And I was wondering, to what extent can the moderation effort of Archive keep up with such themes? Have you thought about how to protect against flooding of information in that sense?
Well, Archive has definitely thought about that a lot. And surely, Ralph, you remember the emergency meeting when ChatGPT became online because stuff started appearing in Archive immediately. And then, you know, it's the responsibility of the submitter to actually take responsibility for what you submit. And so the onus goes back into the submitter. Archive is planning to actually harness AI and large language model to help with the filtering and moderation and the quality assurance, because that's the only way it can scale given how it's growing, which has a lot of potential, a lot of advantages, but also we need to be fully aware, and that's where the Science Advisory Board, it's really aware and, you know, trying to be conservative, because there are questions about data privacy, but also there are questions that you don't want to give everything in the hand of the machine. So the human will always remain on the driver's seat, and the AI just give you tools to actually scale the job. How to do that technically then becomes something that goes outside the scientists, the Science Advisory Board, and more into the team. And I don't know if you want to add something.
No, what I can say at the moment, Archive's rule is you may use LLMs, but you have to honestly declare that you did. In the same way as you have to declare complicated software instrumentation that you used in your paper. And for example, if your English is not too strong and you want to help and have an LLM help you make the language better, that's not a problem. Just confess it. But we deal with tens of fraudulent papers a day at the moment, and that, unfortunately, at the moment, is a burglar and safe problem. We find certain ways to recognize a type of falsification. We learn how to find them and warn the moderators. And of course, as soon as those who submit those falsifications find out that they have been discovered, they find other ways of falsifying. And at the moment, that is a back and forth that, at the moment, I find very difficult to predict where that will end.
Please go ahead.
So I think probably most people would agree that between the Archive and EAS, these are probably the most important research infrastructures we have in astronomy, at least arguably. And I support what you're suggesting, that the Archive would be funded indeed from the EU. So maybe it's this time that people who have good political connections start discussing with the Commission, you know, something which is of order of 10 or 15 million euro a year investment in something like this, which would be a significant.
I think we wouldn't need quite that much. We're thinking about it.
Well, between, I mean, given the vulnerability of the ADS at the moment, I think if you combine both of these, it might be a worthwhile.
Yeah, that might be.
That's the right amount, yeah.
So, but what I wanted to ask you was, when you said that there would be a 24-hour delay, an additional 24-hour delay because of the need to globalize the effort, one could in principle envisage a different route, which is that you could leverage the globalization and actually reduce the time. So instead of having you could do it twice a day or even 3 times a day, have a publication of the Archive.
We have not completely decided on what the model would be. At the moment, we would still favor releasing the papers in batches. Again, in order not to make this a fight over who publishes a paper 1 hour earlier than someone else. So there's always a bit of a balance between making sure that there is enough time to have no micro competition and hurry, and have a calm checking of each paper before it gets let out, versus trying to be even faster than 24 hours in getting everything out. So we'll have to see where that goes.
Thank you very much. Yeah, further questions?
In the 30 plus years of Archive, did you face any resistance from any publication houses? And if so, how did you overcome that?
So I can say something before you came on board. So at some point, Archive went through a little bit of a crisis because it was growing and the resources were not scaling. And that's where we were really worried that the publishers will actually want to phagocytate. There are representatives of publishers in the Institutional Advisory Board and Advisory Council. These are society publishers. There is a difference between for-profit publishers and non-for-profit publishers. So the ones that are actually there are non-for-profit publishers. And so we try to go hand in hand and learn from each other. But there was a point where we saw it coming, but we were aware enough that it was not a danger.
Yeah, so what I would say is that I think the culture in archive itself has grown up where publishers now by default accept that preprints exist and that distribution is free. Even some journals that until 10 years ago still wouldn't allow you to send out a preprint now do. There are fields where it is different. In some fields, finally some kind of an archive has been created, but it is much more owned and dominated by commercial organizations. And we sometimes get difficult questions from parts of those scientific communities whether archives should not try to run an archive of their field in parallel so that it becomes less commercially controlled. And then the question is whether we want to start a war within a field or not. So far we haven't, because we simply do not have the resources and energy, but at some point that may happen. We are hoping that in a more peaceful way a consensus about what the status of preprints should be can evolve.
But I hope the war is not archive. It's the community that decides that their modus operandi is different. They embrace preprint, and then archive becomes an infrastructure for them. Rather. Yeah.
Also, the uptake is very different. For example, bioRxiv and medRxiv spend more time per paper to do checking and some reviewing, but they each publish only a tiny fraction of the total paper volume in their field. Whereas in mathematics, physics, and computer science, including astrophysics, the vast majority of papers appear on archive.
Okay, thank you. And we have time for one final quick question. I see over there at the back.
Thanks. Regarding LLM-based fraud and the question about referee systems to journals, since I'm a board member of the ANA journal, I wonder, doesn't it still have an impact if a paper is downloaded in archive, if it appears in a classical journal or not? Was this ever investigated if the numbers of downloads is, for example, more frequent if you publish in monthly notices ABJ, ANA or so? So that there's a kind of trust in the community that when you undergo the referee process, that also the science content is trustworthy.
We don't check this kind
We don't check. One thing that I would say that is very important is that there is a legend that if you submit your paper to one of the well-known journals, you automatically get accepted in archive, and in some other journals not. Archive actually has a very strict legal principle that is really enforced, that we are independent of the journal. So any paper you submit to archive gets seriously judged, and it gets accepted or not. And all major journals have had complaints that we refused one of their papers. And this happens occasionally, because sometimes it's an edge case and human beings have different opinions on a paper. And it's also true that some papers that are published in very poor journals, because that's the only thing the author can reach, it's still a good paper, we accept it. So our judgment is required to be completely independent of the journal destination intended for a paper. Yeah. And that's a principle we try to strongly adhere to.
There is a little exception, right? That sometimes when a paper is rejected, then the authors appeal, and then sometimes the answer is, I will reopen the appeal once the paper gets through a peer review and get published. But this is because of the field doesn't have moderators that are expert enough in that particular research area, and therefore this gets imposed. But each submission get looked at independently.
Yeah, so I mean, you can appeal a rejection. One of the criteria for the rights for appeal is if your paper is accepted by a journal, we can look at it again. Unfortunately, the range of levels of journals is so highly different that we can't say if you get published, you will be accepted.
Yes.
Right? Because nowadays, some journals, as you all know, all they require is for you to pay the APC and they will publish your result no matter what the quality is. So we do keep a quality check. But it is a reason for reappeal because referees look at papers more carefully. So certainly if you submit to a carefully refereed journal, your chances that an appeal would be accepted are reasonable.
Okay, thank you very much for your presentation and answering all these very interesting questions. And with that, we proceed to the next session of the plenary.
Thank you.
So if you have questions and comments, just come and find us.
Good. All right. Good afternoon, ladies and gentlemen. My name is Mark Kennedy. I'm the chair of the hosting committee, and I'm going to be the chair for the rest of this plenary session. We're already about 5 minutes behind schedule, so rather than go on a 5-minute introduction, which I surely could do, I'm going to make this next introduction nice and quick. Our next speaker is Bruno Leibengut from the Technical University of Munich. Bruno was the Director for Science at the European Southern Observatory up until his retirement a couple of months ago, and I'm sure he's a face and name that is familiar to many of us. So if we can all please welcome Bruno to the stage.
Very well. It was a very exciting discussion about archive, and I think it sort of is a good introduction into what I would like to do. So as a start, you train as an astronomer, astrophysicist, you work as an astrophysicist for many years, and then you get up on stage and they ask you to talk about the future of European astrophysics, and I don't know how that works. So the first thing I thought, I'll use a quote. So I looked this up. So it's difficult to make predictions, especially about the future. Now, this quote, when I knew about this, was attributed to Mark Twain. So I thought, as a scientist, I looked this up because I haven't read all of Mark Twain. So I looked this up. It turns out it's not Mark Twain. Well, we don't know. So this link at the bottom gives you a full story where this showed up. So this is a Danish quote. It's first documented in the 1930s in the Danish parliament. And so for some reason, it was then attributed to Niels Bohr. And this website is very nice. It goes on and on and on, how this attribution goes to different places. So Yogi Berra, as most of you know, was a baseball player in the US. And I think most quotes end up with Yogi Berra in the end anyway. So on that failure, I thought, what do I do next? So this is my trying to predict the future, in particular of telescopes and astrophysics. You will see this coming back. Now, so the next thing I thought I use a scientific method, which is called forecasting. And so 2 weeks ago, I got out my app, I looked up the weather in Cork, and so 2 weeks ago, we were supposed to have 8 hours of sunshine, it's right, 8 hours of sunshine today. I think the temperatures are very close to what it is. This actually works amazingly well, these forecasting things. Now, I want to make in this talk a distinction between predictions and forecasting. Forecasting is a way of extrapolation that we all use. And so I will talk about some of the forecasts of what we're going to do, or what I think European astrophysics is going to do in, let's say, the next decade or so. These are mostly things that are approved, that we know, we hope, we think they're going to happen, or people have committed that they will happen. And then I venture some predictions beyond that. I will also have a few general remarks about the field and where I think we need to pay attention. Okay, so this is the forecasting we want to sort of surmise the future. we have an amazing situation. The last few decades have been fantastic for astrophysics. I will come back to this a little later. When I started, the only catalog that we had was the Palomar Sky Survey, which was on either photographic plates or on film. And so that has changed. I put up some results here. You all know about them. I don't need to go through them in great detail. There is another aspect here, which is, so there's frontline science, front page science, but there is all this other science beneath it that we all do. None of us, or few of us, get up onto these frontline pages, or some of our results do, very rarely, maybe once in your lifetime if you're lucky. But it's important that we do all these other things. When I started, the field that I started in was a backwater field. Nobody cared about these things. There were a handful of astronomers who were dealing with these objects, and that changed completely once somebody figured out, say, well, you can use them for distances or something. The other nice thing about our field is that we do have questions that are continuing. Okay, so we're not sort of exhausted and we don't know what's going to come next. This is part of my field. I know there are many, many more questions that are out there. And so I think this is another very important thing, that we're not out of ideas and that we can continue with very good science. So look back. So this is from the Astronet Science Vision Report from 2007. This is just one picture. It's a long report. It suggested that the ELT should be built. It suggested that SKA should be built, and many other things. But this is a picture that they put up of ground-based observatories, space observatories, and then the planned observatories. And if you look at this, I'm sorry, it's a bit blurry, but you know, the past is always a bit blurry. So if you look at this, many of these observatories still exist. They're still the main drivers that we do. I find the planned section at the bottom very interesting. So there's some observatories that have already stopped working. So they were planned in 2007, just two decades ago, and you know, their lifetime has been less than 20 years. So this is the situation today. And I've been very liberal. I just put everything on that I think there's a European connection one way or another. So there's VLT with the interferometer. There's the IAC, the GTC, it should have been the GTC, HET, SALT, LBT. These are all major observatories, 8 to 10 meter class telescopes that Europeans have access to. Just to go back, the generation before us had access to a single telescope, typically. There's a telescope here on the campus, right around the corner. You know, if you worked in Cork, that was the telescope that you could use 50 or 100 years ago. Okay, and so that's completely changed. Our field has changed. Like archive has gone global, you know, the field has gone global, and we have access to many of these telescopes. We essentially can write proposals for all of those. So at the bottom, I have Alma, Noema, and then Bear Castle. I thought, you know, I should put that on, the largest telescope in the world at some point. This is the LOFAR station at Bear Castle. And then I put, because some of those observatories are so distributed, you can't get them onto one picture, so I just put them down as names. But this is going across the electromagnetic spectrum in various different ways. It's covering the parameters space in a unique way. And we all have access to this in one way or another. The same goes for space. I don't want to dwell on this too long because ESA has a session, has a stand. Go and talk to them there. I put down eROSITA and Integral, even though both of them have stopped operating for you know, different reasons, sad reasons in both cases, but so that's the case. So go and talk to, there's various sessions on these various telescopes. So that was sort of the European angle. I thought I'll put in the global angle here as well. We can read through this. Again, most of these observatories we have actually access to if we wanted to. And if you don't have direct access, there's always the way to collaborate with people. Okay, my Keck proposal actually failed because they said, "Oh no, this is a European," but that was 30 years ago. Okay, so those things have changed. The Vera Rubin Observatory I put on here since yesterday. This is an operational observatory. It takes another half a year until they really start producing the data, but it's really fantastic. You see how these many observatories come together and help us. I put this under forecasting. Now, we just heard about the archive. It turns out we're all relying on services that we just take for granted. The archive, as we heard, is $2 million a year. This is not, it's 300 people working on this. This is not something, we just submit our papers there and we think, okay, it magically appears. But there are people behind this and there's money behind this as well. And so that's important. So we have the archives. Maybe I should put this picture here at first. So I just mentioned the Palomar Sky Survey before. This has changed, okay? You now take a wavelength. This is just 4 different wavelengths. So there's the Gaia map of the sky, Planck, and then 2 X-ray maps, Rosita and Fermi. This is now at your fingertips, okay? You just go to these archives and you get the data off. And so this goes together with these other services that we have, with the many different archives that actually provide that data to you. And again, those things are investments. When I started at ESO many years ago, there was a discussion with Keck, and some American astronomer said to me, "Why are you spending all this money on the archives? This is the equivalent of a full instrument that you could build for the observatory." And the argument for Keck was, the sky is our archive. If we need to observe something again, we just go back and observe it again. So save the money and use the sky. Well, that's changed, okay? Now everything, many things are archived. They're available. I think it's very interesting. I heard a Euclid talk, and I encourage you to listen to the talk on Friday, Kate McGuire's talk on Friday. The archive is now used, the time domain archives, the Zwicky Transient Facility and the Pan-STARRS facilities, archives, are now used. If you find a new supernova, you go back and see whether it has precursors, outbursts, and things like that, which is fantastic. This is unheard of, you know, well, to me. We heard about the archive, ADS, CDS, NED. These are all services that we use every day, and we heard about this as well. What's the worry if they stop working? Okay. All right, so let me go back to this here. We now have these archives. There's been a lot of work by people to make sure that they have this fair principle, that you can find the data, you can use it, etc. The astrophysics, that was a discussion just a few minutes ago. Astrophysics is in a very privileged situation. It adopted the internet much earlier than most other fields. So the astrophysics journals went online much quicker than most other fields. And so that still shows. The other distinction that was part of the discussion, the other distinction is that our major journals are owned by ourselves. That makes a huge difference. If you are in a field where the major journals are owned by private publishers, it's much harder to disseminate things like, and you know, the archive discussion goes in the same direction than this. And so that's, I think, another big advantage that we should cherish and that we should maintain. All right, been to that. So what's coming? Forecasting. Rubin, you've seen the first pictures that came in yesterday. They're going to take a few months until they get really rolling, and then, you know, data's going to pour in. I don't know how people will handle that, but that's a different story. ELT, this is a picture from a few weeks ago. The 2 shutters, the structure of the 2 shutters are now up. It's going to be really boring because they're going to clad it, they're going to close the shutters, And for 3 years, it's just going to be a closed dome. Okay, so bear with us, bear with ESO that this is going to happen. But this is happening. CTA is happening. The northern array has already 2 or 3 telescopes, maybe 4. So they're starting soon. The southern array is putting down concrete. And so they're going to, and you should go to these presentations tomorrow. Why does it say CTA twice? It should be SKA. I apologize. Okay, so SKA and CTA. And so I encourage you to go to these presentations tomorrow where you get the updates on all those facilities. And then in space, we heard yesterday Plato is going to fly end of next year. Ariel is coming, New Athena is coming, LISA. These are all European missions. I wanted to shout out to ESA. These past ESA missions have been scientifically absolutely fantastic. Okay, Gaia, Planck, Euclid, those are changing the way we're doing astrophysics. And yes, HST and JWST, which Europe is also part of, are also fantastic. There are these flagship observatories. But I think the science legacy that Gaia and Planck and Euclid are leaving behind are at the same level as HST and JWST. Sorry, personal opinion. All right, so plan the future. One thing that I think we need to say here is we do need to network as much as we can. Okay, so there is the EAS, very important. And I have to congratulate the organization of the EAS, because when this started as the joint European National Astronomy meetings over 20 years ago, it was, that room wouldn't have been full. Okay, it was a very small start, and it's come a long way. Astronet has been influential at many levels to just plan ahead, to think about what's coming. And so if you hear about this, if somebody approaches you, there's a session tomorrow about Astronet, go and think about it, because not everything that's said in there may come through, but it is important that as a community, we get behind things. There were things like Opticon RadioNet, ACME, ESFRI, Aeroforum. I'm sure some of you don't know what ESFRI is, some of you don't know what Aeroforum is. Let me tell you, if you're not on the ESFRI list, it's almost impossible to get European funding. I mean European national funding for a major facility, okay? And so those are important things. There's another thing that I would sort of bring up is, we've taken it for granted that the community, the society supports us because we're doing the right things, we're doing great things. Well, we need to think about this, how we get that support from now on, because the pressures on what we're doing are increasing, and I'll come back to this. Now, the other thing is, of course, science first. So we need to make sure that the science that we're doing gets to lots of people, not just ourselves, but to lots of people, and that they understand why we're doing this. So, science themes, this is just sort of wrapping up. Astronet, as I said, has been doing science vision roadmaps, updates to these things, which has been very good. ESA has been doing planning. It has the Cosmic Vision program, which is working through now, and it's going to be finishing with New Athena and LISA. And it already has planned the Voyage 2050. So they have an idea of what the next topics should be that they will focus their missions. There's national decadal reviews, there's special publications, I'll show you some of those. And as it turns out, the science cases are very similar. There's specifications, some of them are different, but the core science that we're doing is pretty much the same. So it looks like this over the years. People produce paper over and over and over again, and so it's one report after another, but they are important, okay? They're important, and if they come out, read them, see whether you agree or you don't agree. So what's the plan? Now this is now starting to become less secure, that's the prediction. There's several workshops and conferences here that are dealing with things that people want to do for the future and they're planning for the future. So this is a list of projects that I heard of, that I've been hearing from people. So ALMA 2040 at last, the WST, kilometer-based optical near-infrared interferometry, the time domain telescope. These are discussions and people are trying to sharpen their science cases to why these telescopes should be built. Voyage 2050, I mentioned this. So the Voyage 2050 is looking at moons, or suggests to look at moons of giant planets, temperate exoplanets, find life, this is the thing, and probes of the early universe. I wasn't quite sure what they mean by that. There's other space observatories that are being talked about. In the US, it's LUVAR and HABEX, and in Europe, it's LIFE for exoplanets. ESO has started a process which they call expanding horizons. This is trying to find out what should ground-based astronomy in Europe look like in the 2040s, okay? And so there's a workshop tomorrow and I think on Thursday, so I encourage you to go there, listen to this, see whether you like it, and support it when you like it. There's plans for gravitational waves, there's plans for neutrino detectors. I wanted to make that point as well. We're astrophysicists, and I think it's becoming more and more important that we convince other physicists as well that this is the right thing to do. If you're not careful, then these particle physicists, who are extremely well organized, walk into your field and take it over, as I experienced, okay? So it's important for us to make our point that we do physics, and some of the physics that they would like to do, you can only do in the sky, okay? All right, challenges and threats. I thought I need to bring that up. We have a number of things that are coming up, and it's been getting worse daily, almost. So there's a workshop on the environment, sustainability. Are we doing the right things? Yes, thank you. And so we need to think travel. Observatories need to think about their footprints, CO2 footprints or equivalent footprints. Computing, we just take it for granted. You know, there is computing. There is Google. There is the ADS. You archive. You just submit your things and it comes back for free. Well, as we all know, nothing's for free anymore. And so we need to be conscious about these things. And I think we need to be good citizens in doing this. Pollution, I'll show you a couple of cases, but we're now struggling with the fact that our pristine sky is being polluted by other people. And what are we going to do about this? So I'll show you about a few things. Societal demands, it's been great and it's been fantastic to talk to ourselves, but we also need to get society behind us again, I would say. We're doing pretty well. We're probably doing better than many other fields, but it's not so obvious for the public that what we're doing is as important as medical science, for example. So these are things that we should look at and we need to think about. The other problem that I have been experiencing over the few years is that people start questioning our methods. After the pandemic, there's more and more people who don't believe what we're saying anymore. And we need to go back out and convince these people, not just them, we need to convince everybody that what we're doing is important for society. It's been fundamental for progress that we had over the last 100 years or more. Light pollution, I just wanted to flash 2 or 3 things. So this is the light pollution as predicted. So this is today. This is over the Vera C. Rubin Observatory. And this is coming from space debris in low Earth orbit. So we have more and more satellites in low Earth orbit. If these satellites just create dust specks or loose paint or, God forbid, collide, okay, you get a lot of debris in the low Earth orbit. And that debris will scatter and it will increase your sky brightness. So the picture on the left is 2024, and the picture on the right is a prediction of 2025. So that's just appeared. Another more specific case is this here. So if you think about Paranal in the Atacama Desert, you would essentially think it's the end of the world. Nobody's going to come there, and it's literally been true for many, many years. Well, there's now a plan, a proposal to put a several gigawatt photovoltaic and wind farm plant there to create hydrogen, green power, okay? The hydrogen will be converted into ammoniac to be transported down to a port. This all would be built. And if you look at this, it's right next to the CTA place. Now, the Cherenkov people are not observing during moon because the sky is too bright. Now, if you then put a plant right next to it with lights, then your sky is going to get brighter, and it's going to be a problem for them. So this is a picture of Paranal. You see the various things. This is zodiacal light. Okay, so this is not actually human-made, but you see this here. So this is on Augusta, which is 100 kilometers away. This here is a mine, a copper mine, the biggest copper mine. This is another 100 kilometers away. And here's a small village, Barbosa Tal, 20, 30,000 people. That's much closer. And so that's the sky on Paranal right now, or 2009, some years ago. That's the sky brightness over Paranal 2012. Oops, that's what I should. So you see these spots here. So there's Antofagasta, there's Escondida, there's Tal, which you barely see. Now, in 2024, it's already increased by a couple of percent. And what you also see here is a wind park that's nearby. So if you're on Paranal right now, you see in the distance blinking lights from windmills, okay, wind turbines. And if this project that I described becomes fully implemented, then we actually lose another few percent on the sky on Paranal. You know, that could have impacts like there was a recent near-Earth asteroid that had a probability or a small chance of impacting the Earth. And they did take astrometry with the VLT, and you know, as usual, it wasn't an impactor. But if you lose the ability to see things like that, you may actually you lose your ability to forecast impacts. All right, so for me, I think it's really important that we coordinate things at all levels, okay? So I've experienced community collaborations where the community organized itself to make best use of the facilities. I put some of the names here up, and that's very good. I think it's also very important that the facilities keep on talking to each other, that they do coordinate. I know they do, SKA and ESO and SKA CTA, they're all in contact very much, so that we do that. At ESO, we try to put in these joint proposals, VLT, VLTI, and ALMA. The uptake has been slow, if I may say. I think that could be a thing. XMM Newton and VLT, that's an ongoing joint proposal process. We get 2 or 3 proposals, very small, the uptake there as well. And I think the US is doing that much better. I do think, looking down here to the EAS, I think the EAS has a fantastic role in coordinating community. And so the various workshops that we have this week, the workshop on the future of astronomy tomorrow and Thursday are examples where I think the EAS has a real important role to play. And as we heard yesterday, it's doing this also with the EU, so that's good. Success factors, scientific excellence, I can't even spell scientific. Scientific excellence, education, innovation, creativity, I think we need to keep on going. This is when I think about artificial intelligence, I'm having a hard time fitting that in, but I'm an outgoing generation, so it's for the next generation to work this out. As you clearly see, I did not use any artificial intelligence here. Superior facilities, that's been a key over the past years, past decades. If we have great facilities, energies, all energies, energy resolution, I mean this for all messengers, sensitivity, angular resolution, these are, in most cases, these are winners, but these need to be discussed. Computing, data availability, we mentioned all this. Stable financing. We've really had a fantastic time where we did not have to worry about money. It just seemed to be coming. The national governments seemed to be okay. The European Union put the European Research Council in place. There was a lot of money coming that way. We may have to work for this in the future. We actually may have to go back and convince people more that we're doing the right thing. But in the past, this has been a guarantee that we actually succeeded. And that also is true for facility development. You know, the fact that ESO has a stable financing over 20 years to build an ELT is absolutely key. And that was true before for the VLT and ALMA as well. All right, so here's my conclusion. It's not very innovative. We need to talk. We all need to talk to each other, but we need to talk to the people outside as much as we can. I talked to Anja Andersen yesterday, and she told me she's been talking to heavy metal at a heavy metal festival and convinced people that, you know, told them where the metals are coming from. That's the type of thing that we need to do. Okay, so we need to talk to also the people who don't want to necessarily hear us, but we need to tell them. So I think we have a task to go out and talk to society more than in the past. I know people do this, but it's more. And we need to do this at all levels. Education, politics, we need to talk to government. In education, you may have a future minister in your class. Think about this. And make sure that that future minister, when he or she gets, or they get into this position, that they will remember your class and support astronomy in the future. I mentioned briefly, we also now are a bit under attack for our sky. We may be getting into a situation where we lose access to the sky, which I find staggering. I find really scary. And the last thing is the future is defined, is being defined now. Go out and get your voice in so that hopefully you get what you want. Thank you.
Thank you very much, Bruno. In order to keep on time, we maybe have time for 2 quick questions, if anybody would like a question.
Thank you very much, Bruno. I wanted to come back to one of the points you made, which is, you know, the competition/collaboration with particle physics, right? So, do you think there's a way to think of the future as more coordinated effort with that community? And, you know, I'm thinking even expanding horizons. I mean, you know, is there something we can do together? Some of the questions are indeed common. Wouldn't we not benefit from collaborating with that community, you think?
Oh, absolutely. And I'm trying to think of the best way how to do this. My personal experience has been through the university, for example. There are physics departments that have particle physics and astrophysics. And, you know, those are the first connections that we have. And then we need to go from there. But it's also, so Astronet, there's an equivalent coordination network, which is called APEC, for astroparticle physics, actually. And so we need to, I should have put them up, we need to, you know, talk to them because they are putting up the neutrino detectors and the cosmic ray detectors. And so there are more and more overlaps with these communities and we need to keep on talking. Yeah.
One more very quick question. Okay, in that case, we could thank Bruno again, please. Okay, our next speaker is Alkisti Bonanos from the National Observatory of Athens, where she's a research director. And on the topic of European Research Council grants, she's going to be talking about the results of hers on evolved massive stars. So please, Alkisti.
Hello, everyone. It's a great honor and pleasure to present to you on episodic mass loss in evolved massive stars. Let's get started. So, massive stars, what are they? So, they're stars with initial masses above 8 solar masses. They're fascinating, powerful engines that impact the evolution of galaxies and the universe. They end their lives in powerful explosions, which form neutron stars or black holes. So they have these powerful supernovae, or core collapse supernovae are the end states. They are also the progenitors of gamma ray bursts. Massive stars tend to be in binaries, so if you have 2 massive ones that form 2 black holes, they'll be the progenitors of gravitational waves. We also know that the first stars were very high mass, so massive star physics affects the early universe. And they also explode. We think they exploded in the early universe too, so they form dust and are important for the chemical enrichment of galaxies. Let's take a look at the HR diagram. We're looking at the upper part of it. So this is an HR diagram from Ekstrom et al. Showing evolutionary tracks for massive stars. And I've placed the locations of the massive star zoo. So there are very many types of massive stars, which we're trying to figure out how they hold together and how one is connected to the other. We have red supergiants on the right, so going to the yellow hypergiants and yellow supergiants, yellow hypergiants being more luminous. In the blue, we have luminous blue variables and blue supergiants, and the peculiar supergiant B bracket E stars, and the extremely blue, normally stripped, are Wolf-Rayet stars. We notice the Humphreys-Davidson limit with a black line at the top. That's the limit above which stars become unstable as they reach the Eddington luminosity in the outer layers and they start losing mass. So you don't typically find stars there. Now, there are many parameters affecting their evolution of massive stars and what makes it complex. So mass is the main parameter, but then there are other parameters that come into play and are quite important. So there's rotation, which spins up the star, helps mix it up. If it's rotating very fast, it can lose mass on an equatorial disk. There's convective core overshooting, which causes mixing. So the convective core can bring in material from the radiative outer layers, and that increases the hydrogen available and extends the main sequence life. Metallicity affects the evolution, especially in the hot stages. The mass loss happens through line-driven winds. Then there's mass loss, which happens at various stages, not only the line-driven winds when they're on the zero-age main sequence at the beginning, but also post-main sequence phases might have supra-Eddington thick winds, like might happen in the LBV stage or the red supergiant stage. We're not sure. It might be happening there. And finally, there are also magnetic fields that have been detected in massive stars that could be affecting the evolution. And there's also binarity. We know massive stars come in multiple systems, binaries or higher order multiples, and those definitely affect and increase the parameter space and the complexity of modeling their evolution. Now, we used to think red supergiants explode as supernovae. Then after supernova 87A, we know that blue supergiants explode as supernovae, also Wolf-Rayet stars, but in the recent years, we've been finding LBVs and yellow supergiant exploding as well, which were not these were not expected to be exploding. These were thought to be intermediate stages as stars are evolving. So let's go to episodic mass loss. This is from a review paper by Nathan Smith in 2014. It's still current. He states that the luminous blue variable eruptions and pre-supernova eruptions are a major unsolved problem in astrophysics. The physical mechanism is not understood or accounted for in evolutionary models. So keep that in mind when you're using models to look at galaxies or the early universe. These things, there are phenomena existing that are not taken into account. So this is an HST image of Eta Car. Perhaps you know it's in our galaxy. It's a luminous blue variable that in the 19th century lost 20 solar masses, but it was not a terminal explosion. There's still a 100 solar mass star there, and it has a 30 solar mass companion in a 5.5-year orbit. So these are complicated. This bipolar outflow, we think, happened from back then, from the 19th century eruption. From the same review paper, this figure shows the mass loss rate. So our current knowledge of mass loss at solar metallicity for various types of massive stars, various stages. So we have the O stars, the Yahya relationships here. For red supergiants with the red lines, we have some curves. These are mostly empirical. Some are theoretical curves as well. There's a line-driven limit in the silver line up here. LBV giant eruptions are the blue box at the top. That's just Eta-Car, 20 solar masses lost over 10 years, approximately where that falls. That's such a approximate number. There's binary Roche-Loeb overflow as well, approximately here. And you see there are orders of magnitudes differences in these relationships. So we'd like to know, what is the frequency of major mass loss ejunctions like Eta-Car? Does it depend on metallicity? For red supergiants, what are their mass loss rates, and do they depend on metallicity? And finally, these B bracket E stars, these supergiant B bracket E's, what is their evolutionary status and how frequently do they occur? Now, there's a lot of evidence, both from the massive star community and the supernova community, about episodic mass loss being happening in nature. So Spitzer, in 2010, Spitzer data revealed circumstellar shells or bubbles, these nebulae, in the galaxy. When people took spectra, they found evolved massive stars. So Wolf-Rayet stars, luminous blue variables, showing up with bubbles, these nebulae, so mass loss. Also, high-resolution images of known massive stars like LBV, luminous blue variables, red supergiants, the fried egg nebula, a yellow hypergiant, and another one, show all these remarkable structures and features, definitely not symmetric mass loss. They're bipolar features, random ones, or maybe multiple eruptions. So these are all pointing to stars losing mass via strong stellar winds or instant outbursts. From the supernova side now, we know about interacting supernova. We have this type 2N that have narrow lines indicating interaction of the blast wave with a dense circumstellar material. And perhaps one of the most famous examples is supernova 2009 IP, a luminous blue variable that went supernova. It was named in 2009 after its first outburst, but it turns out it wasn't the final explosion of the star because it had a second one and then the third one a few years later that was thought to be the final eruption. Now, there are also dusty superluminous supernovae that have been found to occur at low metallicities. Supernova 2010 JL is a very famous example of that. Then there's supernovae imposters. So they were called supernovae, but then just like this one, they did not erupt. The star was still there. They did not, completely explode. And then there are red dusty optical transits as well that show evidence for this episodic mass loss. So what is happening here? What is this phenomenon? It's still unclear. Now, massive stars that lose mass form dust, and they're bright in the mid-infrared. So what I'm going to tell you now is this project we undertook to study episodic mass loss using this fact that they're bright in the mid-infrared. The left plot here is a CMD using Spitzer data. What we did is we took known stars in the LMC, stars with spectral types, so we knew exactly what they were and saw what their Spitzer colors were and put them on the CMD here. And we found that red supergiants, LBVs, supergiant B bracket E's, are the most luminous sources at these wavelengths. Another interesting star is Object X. This is the most luminous star in M33, and it was discovered only in 2011 when we looked at it at Spitzer, because in the optical it was obscured. But if you looked in the mid-infrared, whoa, you have this whopping SED here, very similar to VAR A. This is also extreme hypergiant in M33 that was in eruption. It lost a lot of mass, and IRC 10 plus 10420 in our galaxy, that's also an extreme hypergiant that's undergone episodic mass loss. So here's where the ASSESS project comes in, ERC-funded grant that unfortunately ended last August. I was very spoiled. The aim was to determine the role of episodic mass loss in the evolution of massive stars. So there are 4 things we set out to do: to find these objects using machine learning and try and classify them. Then to make a big campaign to survey them, and the idea was to get 1,000 spectra of these dusty evolved massive stars spanning a range of metallicities. Then to do modeling, SED fitting, and spectral and atmosphere modeling to measure the parameters and mass flows for all these stars, and finally compare with evolutionary models and reverse engineer the stars to determine the mass loss rate. Here's a picture of the team 3 years ago, actually, almost exactly 3 years ago, in Ireland, Ballyconnell, Ireland, where there was an IAU meeting. Yeah. So the first step was the machine learning photometric classifier. So this took a bit longer to develop than initially envisioned. We developed a photometric classifier based on color indices, actually 3 machine learning algorithms. We took the result of all 3, and it has an overall accuracy of about 80%, and for red supergiants, over 90%. So this was developed by Grigoris Maravellas. The classifier now, we've applied it to over 1 million sources in 26 galaxies, spanning again a range of metallicities, and we've produced this catalog, so it's under review, this paper, with robust classifications for over 275,000 stars. Here's the table. We had the classify things in 7 classes. So red supergiants, yellow, blue, B bracket E stars, Wolf-Rayet, LBV, and then there's a category of galaxies or other extragalactic things that would pop in. Okay, moving on to the survey. Since the classifier wasn't ready at the beginning of the project, we just had to stick to CMD filtering, so we developed this priority system. We would select more luminous and red sources to be higher priority. And then these various priority classes had to do with if they're counterparts in the optical. So we used the VLT, FORS2, and GTC in the north, so the southern survey and the northern survey we had. You can see the breakdown of the number of spectra. You notice perhaps the priority sources. There are 384 in the south. But of these, we had various, not all of them turned out to be massive stars. So in the end, we turned out with a catalog of 185 evolved massive stars in the south, containing a lot of red supergiants, 129. And in the north, 29 red supergiants. So you see the tables show the galaxies we selected. The distances are from about 1 to 4.5 megaparsecs, so that's quite far. Like these are some of these massive stars found at these distances happening for the first time. We have a metallicity range of 0.06 approximately to 1.5 solar metallicities. The northern galaxies are closer by. And that was the largest catalog of stars at low metallicity of evolved massive stars that's been produced beyond the local group. So here on the left is a cumulative color magnitude diagram showing the results from the southern survey. So they're color-coded by spectral type. So these stars have all been classified with a spectrum that we obtained. So we have a lot of red supergiants. You see the red circles. Unfortunately, there were a lot of H2 regions. Actually, these might be good for some people doing H2 region studies, but we had a lot of contaminants in M83 and the more distant galaxies and ones that were a bit toward edge-on. The dotted line shows the priorities. So the high priority systems are in that box, the ones that are dusty. On the right, I have a plot showing the modeling results for the red supergiants in the southern survey by Stefan de Witt. Who obtained luminosity, radii by fitting Mark's atmosphere models, etc. So what's interesting to note here is that a lot of them are very luminous. Our criteria were looking for luminous and dusty sources, so indeed we found many, about half of them are above log L of 5. And you might also notice these very extreme red supergiants that we found. WHG64 is noted there. I don't know if you're aware of it. It's an extreme red supergiant in the LMC. There was a press release. It's the biggest star in the LMC. And I'll come back to it a couple of times during this talk. So the Humphreys-Davidson limit, as you can see, is at 5.8, although recently it seems to be revised to lower levels, around 5.5. But here we have some stars that are pushing that limit. Okay, now about the red supergiants, let's look at them in this slide one more time. Looking at the dusty sources here on the left, and the right plot is showing the dusty, basically looking into that region of the dusty red supergiants and showing the spectral types. So what's interesting here is that you do expect the red supergiants going up the Hayashi track to be the most evolved dusty ones, to be the ones going up the Hayashi track. So you'd expect late spectral types. But here are some that are earlier, like K-type stars. So you're thinking, how can that be? Now note that the Spitzer photometry was taken about 20 years before the spectroscopy. So it could be that something changed. Either they're varying. They're spectral variables called Levesque massive variables, or perhaps they experience a Maslow's ejection even though they were K-type stars. So we have a percent, 12% of our K-type sample, something has happened to them. So that's saying something about the episodic Maslow's. We also studied the mid-infrared variability from WISE for all these sources. I don't have time to go into it, just pointing out that some of these luminous dusty red supergiants show similar mid-infrared variability to the progenitor of type 2P 2023 IXF in M101. You might be aware of that, but that was a nearby type 2P from a red supergiant that had 0.4 mag variability in the mid-infrared. So we're finding the same to these stars before they explode. Moving on. We said one of the things is the Maslow's rates of red supergiants, which are quite uncertain. So Ming Yang, who's a postdoc in the group then, undertook a survey, actually made a catalog of red supergiants in the LMC. Each point here is a measurement of the Maslow's rate of a red supergiant. What we did is the result of fitting the SED. So there's a lot of photometry for the LMC, very good quality, so we can fit it and with a dusty code and obtain a Maslow's rate result for each one of these. Of course, there's several assumptions going into this. He assumed the main one is the radiatively driven, the profile of the winds. All the lines here you see are coming from the literature, so literature results, so it's a mess. They also differ by several orders of magnitude. Now you might say one of the most important things is that we find an upturn, a kink we called it, at around log L of 4.6. This had not been seen before. Now we have a large sample of stars. Previous studies were based on smaller stars. Now we can do it with more stars, so we've done it here. And you can compare it to the plot I showed at the beginning. They kind of in between the Van Loon and Yahir relationships here. Kostas Antoniadis, my other PhD student, repeated this work for the LMC. The previous one was work with the SMC. Now let's go to the LMC, higher metallicity. Let's see what we find. Again, he obtained photometry, did the SED fitting with dusty, blah, blah, blah. And here's the result. Again, an upturn. The points here on the left with circles have spectral types, so we know for sure they're red supergiants. They're not only photometrically selected. The kink is a bit at lower log L this time. And there's a big difference now. Kostas investigated more the assumptions and used the steady state winds, which turns out to be probably a better approximation. So the velocity of the winds is constant versus accelerating. And this lowers it has an effect on the Maslow's rate. It lowers the rates by 2 to 3 orders of magnitude. So finally, we understood why in the literature there's so many different values. So it depends on this assumption that they used for this. So we're measuring it based on the dust. There's also gas to dust ratio assumptions that have to go into it. And this assumption was quite important. So comparing with the red curve from Ming Yang's from the SMC result up there, now we're lower. So if we can't get rid of the envelope of the red supergiant with proper red supergiant winds, how do you get rid of it? So it seems like episodic Maslow's is, again, even more important, or we need binarity or some other effect to get rid of the envelopes of the stars before they explode. The next obvious thing to do was to do it for a range of metallicities, to go to higher metallicity. But it was hard. In the Milky Way, you don't know distances well. We tried to do it. These are the black points. NGC 6822, there's some James Webb data on that. Of course, it's for a very small field, not very many red supergiants in there, but we did that as well. There seems to be an agreement. There seems to be no strong correlation with metallicity so far, but we're working on this with a better sample with James Webb data for other galaxies. But indeed, we find this kink, so enhancement of Maslow's at high luminosity, and that Maslow's rates are lower by 2 to 3 orders of magnitude. So that's something to keep. And as we said, evolutionary models are not using these lower, they're using other Maslow's rates. Also, I wanted to finally point out the work by Dessin in 2024. They used gas diagnostics. So they studied red supergiants with ALMA, probing the gas. So this is the bulk of the material. And their results are actually up here. So they're in agreement with what we're finding. So that gives us confidence that this is in the right direction. Finally, Manos Zapartas, who was a postdoc in the group a couple of years ago, investigated the effect of the Maslow's rates in evolutionary models. So he computed new MESA models generated using Maslow's rates, so 4 different Maslow's rates. So by these studies over here, The Beezer study is observational based on red supergiants in clusters. The K relation is based on an analytical model based on turbulence. So using the Poseidon platform, Manos has come up with this HR diagram, which is a bit complex. I'll walk you a bit through it. So he's made these contours. For example, the blue here, let's look at the blue. That's based on the results of the Yang winds. And the stars show the locations of where core collapse is supposed to happen according to the models. And then we compare that with observations, which are the points with the big error bars. These contours take into account the IMF of the stellar progenitors, weighted with the star formation history of the SMC. So he's done as careful as a job as he could with these predictions. The Beezer model is here, the Ya here, and the K result. So the key result we see, oh wow, is overstripping the stars. So it's not really an agreement. Basically, none of these agree very well with the data. So more work needs to be done. Moving on. Right, so the last part of the talk, I want to focus on two very extreme and spectacular stars, red supergiants in the Magellanic Clouds. The first one is LMC3 or W60b90, an analog of this red hypergiant I mentioned before, WHG64. It's all the way up there. The models don't reach it. It shouldn't be there. There shouldn't be a star up there. It's actually pushing the limit for hydrostatic equilibrium and the Eddington luminosity. So it's unstable for radiation pressure and for hydrostatic pressure. Now this drew our attention because there was an HST archival image here on the right showing this interesting bar feature that resembled the structure around Betelgeuse, which has a bow shock. So we actually did find with Gaia data that it is moving in that direction. We took spectra, there is shock material, but I don't have time to go into that. What I want to focus on is dimming events. So you've probably heard of the great dimming of Betelgeuse back in 2020. It dimmed by 1.25 magnitudes over a few months, and it lost 3 to 120% of the annual mass loss of Betelgeuse during that event. What we think happened is this convective plume that can happen in a turbulent atmosphere can rise and break free from the surface, powering an upwelling that becomes the surface mass ejection. So this cartoon demonstrates it nicely. Basically, this plume came out. As it cooled, it formed dust, and that was in the line of sight to Earth, so we saw a dimming event. W60b90, is it a massive analog of Betelgeuse? Well, Gonzalo Munoz Sanchez, he just finished his PhD a few months ago. He compiled this 30-year light curve from archival data, Macho, Assassin, Ogle, Gaia, Atlas, for example. The upper plot shows the light curves, the lower one shows relative light curves, just so you can compare between the various bands. And indeed noticed 3 dimming events. 1, 2, 3. Looking at them all together, the colored points are the ones for W60b90. We see sort of a occurrence every 11.8 years. And what we measured is the rise time. So from the minimum, how long it takes for the light curve to recover. So about 400 days. And the depth was about 1 magnitude. Now compare that to Betelgeuse, shown in gray. It's very different. Betelgeuse recovers in 200 days, and it's a little bit deeper. So then we thought, what about other red supergiants? Does any other red supergiants show this? So we found some data from USEP showing the depth that was wide, just like the one for W60b90, and the RWSEP. So these are both red supergiants that especially RWSEP matches amazingly well. I mean, this is just pulled out of the archive and overplotted, and it looks identical. So how could this be? So we thought size. Maybe the size of the star has something to do with this. Now, the galactic sources don't have very well measured radii because the distances are uncertain. But Betelgeuse seems to be smaller. W60b90, since it's in the LMC, has a very good size measurement and a good distance. So we think that the rise time probably depends on the size of the star, because if this convective plume is covering a large surface of the star, it has to do with the recovery time of the star after this convective plume escapes. So the question arises, is that true? Can we calibrate this relationship? Can we use a light curve to measure the size of a red supergiant? That would be really cool if we can do that, so we're working on that. And how common are these dimming events? With Betelgeuse, we thought they were rare, but now maybe not. Okay, moving to the last object. I told you I'll come back to this one, WHG64. This is an extreme red supergiant, and we found this quite amazing result. Gonzalo Agyan compiled archival light curve from the archives. Matcha shows very strong semi-regular variability over 2.5 magnitudes. Ogle, it's decreasing. And then suddenly in 2013 or 2014, something happened. The I band is constant, but the V band jumped by 3.5 magnitudes. And then the variability kind of stopped and is going down. Now, spectroscopically, the vertical lines show the epochs of spectroscopy. It was traditionally known as a very late type M supergiant, M7, M5. But then our spectrum was taken here, showed supergiant B bracket E features. So we're saying, did we take the right star? It was a red supergiant, now it's blue. And we found actually an archival X-shooter spectrum, an amazing quality spectrum that's not been published, that also found it B bracket E. So we can constrain when the transition happened. And with the light curve, we can also constrain it even better. So the bottom right shows the spectra. The brown one is the red supergiant in 2007, and 2016 is the pink magenta spectrum with B bracket E features. So it transitioned into about a year with no outburst or explosion detected. If anyone can explain this, we're very happy to hear your opinions. What we found, it's most likely a massive symbiotic binary. So from the optical, we see these B features, but so what we think is a blue companion is showing up, and the B bracket E might have to do with a transition as well. And the red supergiant transitioned to something yellow, which we see in the near-infrared X-shooter spectrum. So first we thought it was blue, but then we looked more carefully at the near-infrared, and it's actually yellow. So the red transitioned to yellow hypergiant, and there's a B-type companion that just appeared now. Before, the red hypergiant was too bright and we couldn't see it. So the scenario we suggested are partial stripping of the envelope by binary interactions. That's one idea. There's a binary that stripped the envelope. The second scenario is that the star was in a quiescent state. Actually, no, it was it was in an eruption and returned to quiescent state, something similar to VAR A. What happened to VAR A? Or the last scenario is that it expelled its outer layers due to a pre-supernova superwind phase, indicating it's going to explode soon. On the right is an image published a few months ago by Onaka et al. Using VLTI. So they actually resolved for the first time a star in a nearby galaxy. And if they confirm this outer ring, it may have to do with this change 10 years ago, but they're not sure if it's an artifact or not. It seems to match, though, pretty well with this 10-year. If you assume a velocity and how far it should be, it does match up. So we'll have to wait and confirm that. So to summarize, the EAS project has provided classifications for a lot of evolved massive stars in 21 galaxies. We've produced the largest catalog of evolved massive stars, and especially red supergiants and low metallicity beyond the local group. And concerning episodic mass loss, I think we've nailed down the mass loss rates for red supergiants, at least at the LMC and SMC metallicity, and found that they're 2 to 3 orders of magnitude lower than previously assumed. This enhancement at high luminosity, we think, will be found probably well, we'll see, but at high metallicity as well. We find evidence for episodic mass loss in 12% of the K-type red supergiants. Concerning dimming events among red supergiants, we think they're not uncommon, and we found a massive analog of Betelgeuse in the LMC. And finally, I mentioned the spectacular transition of the extreme red supergiant, WHG64, to the blue. So thank you. I will stop here. Thank you very much.
So thank you very much for this impressive overview. My question is also in relation to Bruno's point about the future. And so you have already explored 21 galaxies in the local group and beyond, and have a big sample. But so what would the new facilities bring you, the ELT and JWST?
And James Webb, you said? Well, James Webb for sure. We're missing better mid-infrared data, and that is been a problem. Like we couldn't do M31 and M33 because the Spitzer data are too contaminated. So James Webb should be able to help that, and Costas Odoniadis is actually at ESA right now on a visitor program reducing that kind of data. For the future, variability, LSST will be amazing. I mean, we'll have light curves of thousands of red supergiants. We'll be able to pick them out just by their variability, I think. And I forgot what else. That's, yeah, so... Oh, ELT. Oh, well, ELT, of course, you'll be able to get spectra of a lot of them, which you can only reach some limit of 21st magnitude with current 8 meters, so you can go much deeper and farther. And other metallicities, lower metallicities, for example, that you need the bigger aperture. Thanks.
Hi, thanks a lot, Elsaster, for this great talk. I have just a small questions concerning the G64 object. Could it be that it's just an orbital phase effect, that you are looking at the irradiated side of the giant instead of the non-irradiated side of the giant? Or, I mean, the change of the spectral appearance?
The spectral appearance, no. The light curve may have to do with that before this change, but the change, the transition itself, something fundamental has happened.
Okay.
Yeah, I mean, how do you go from an M-type spectrum to a B-bracket-E?
Oh, we see this in the cataclysmic variables, depending on which orbital phase we are looking at it. But I don't know what the orbital period is, if that could be an...
I think it's difficult to reconcile, but we can discuss. Yes.
Okay, if we could please thank Alexis again. Okay, and for the last part of our plenary session this morning, I'd like to invite on the stage Arunas Kuchinskas and João Alves, who will be presenting the Astronomy and Astrophysics Awards 2025 for the Outstanding PhD and Early Career Researcher article. So I'll hand it over to them.
So thank you very much again. And hello to everyone. It's my utmost pleasure to be here and to present the prizes, A&A prizes, to two young people, some of those of you, and to really actually say that this is very important to us as a journal. And why is that? So the prizes are presented by the board of directors of A&A. At A&A, we really are proud that we call ourselves a journal by astronomers for astronomers. What is meant by that? So, for example, the board of directors, we are all astronomers. We do a little bit of bureaucratic work there. We have to, because we organize things and so on. And one of the tasks of the journal is to look into the future of the journal, into the strategies and how we are going to evolve what we want to do within the next, say, 5, 10 years from now, and also even further in the future. And that's really part of what we do at the board. And from that perspective, we are really looking very much into the strategies, different things that have been mentioned by Bruno, for example, during the talk early in the session, because publication of papers is evolving, just as astronomy does in general. And so that is what we do there. And I will use this opportunity just to remind you that we have a lunch session right after this session, which starts at 13:15, where we are discussing science publication. And from that perspective, it might be interesting to mention that we did a survey of A&A authors where we really were shocked by you guys. I mean, your response to our questions about open access, about science publishing, about AI. It was a huge success. It was a really big thing. João is going to give a talk there, so I'm not going to do any spoilers here, just to invite you there if you're interested in these matters to join. But of course, there's another thing that we are doing as a journal by astronomers for astronomers. That is the young generation. We really know that it is also up to us to do something that could foster, help you, our younger colleagues, in some ways, to make your point, your science better. And so from that perspective, for example, we have scientific schools, we call them SWIA, Science Writing for Young Astronomers. We want to make it a regular event, and it's we have a feeling that it's appreciated by those students who attend, because we really talk about the inner things, about how the journal works. We all publish. I presume that every one of you knows what ANA is, but when you go down inside the thing, there are many intricacies there, and we are happy to tell you about that. So that's why we are trying to do these schools and other things. But among those are the prizes. And so these prizes were all that started actually in 2021. So now it's a 5th edition. And with this 5th edition, we are very proud to present it to 2 people. You will see that in a moment, but I just want to take an opportunity and also say that this is every year. So next call, and it works in a way that you supply, you do actually submit, sorry, not supply, but you submit an application for a prize. There are 2 categories for the best PhD article, and another one is best article of a young career researcher. So you do applications. The application deadline is normally, they are announced in October every year. And then the application deadline is a month later, normally at the end of November. And so, yes, then you have it here. There's a small cash prize, and there probably that is something that doesn't hurt too much, I hope. But important is that we really feel that as being part of the community, we really somehow want to embrace you, younger generation, and really give you an opportunity to present your talk. And so, just to finish, let me just say this. Please, especially the younger ones who are here, and also maybe in other rooms, seeing this on the screens, keep that spark of inspiration, which leads to new projects, which leads to new collaborations, which leads to interesting, excellent results. And that's how you contribute to science, and of course, to good papers, which we are more than happy to publish in A&A. So I encourage you to apply for the next edition, again, autumn this year. And thanks for being part of this great thing, which we call astronomy, European astronomy, world astronomy. Really, you are the future. So thank you very much for that. And now I'll pass a microphone to A&A Letters Editor-in-Chief, who will present the prizes. Thank you very much.
So in the name of the editors of ANA, I would like to call Sarah Masha and Marion Villeneuve to the stage. So maybe a few words about why we think their papers were brilliant. So let me start by saying it's a great pleasure to present this year's ANA Award for Outstanding PhD Article. The prize goes to Sarah Masha for her outstanding work on one of the central questions in cosmology, what reionized the universe. In her PhD, Sarah tackled this problem by identifying indirect indicators of escape fraction, that is, the fraction of ionizing UV photons that manage to escape from galaxies into the intergalactic medium. In her award-winning paper in ANA, based on JWST Sears data, she studied low-mass galaxies at redshift 6 to 9. She calculated their escape fraction and ionizing photon budgets, showing that these galaxies could account for about a third of the total photon budget needed for reionization. The rest, she argues, likely come from even fainter galaxies just beyond the reach of Sears. Sarah's work has significantly improved our ability to estimate escape fractions, and it marks a substantial step forward in understanding a question of profound cosmic importance. Please join me in congratulating Sara Masha. It is also my pleasure to present this year's ANA Award for Outstanding Early Career Research Article. The award goes to Marion Villeneuve for her exceptional contribution to our understanding of how planetary systems begin to form. Marion's paper investigates the vertical settling and radial drift of millimeter-sized dust grains in protoplanetary disks, processes that are critical for the early stages of planet formation. Her work is based on high-resolution ALMA observations at 0.1 arcsecond scale, using continuing emission to directly measure the vertical structure of dust in nearby edge-on disks. She found that millimeter-sized dust is confined to thin layers, just a few astronomical units thick at the distance of about 100 AU from the star, significantly more compact than the gas. In one case, the disk is even more vertically compact at 2 millimeters than 0.9 millimeters, providing the first direct observational evidence for a key theoretical prediction, that large dust grains settle more efficiently than smaller ones and more than the gas. This is a landmark result in a highly active area of research, bringing us closer to understanding how small grains in disks grow and evolve into planetary building blocks. Please join me in congratulating Marion Villeneuve.
Hello, everyone. I promise I'll keep it short because I still can't quite believe I'm standing here. So receiving this award for me is truly an honor because A&A is my scientific home. Since the beginning of my PhD, all the papers I've written have been published on A&A, and so having an award for one of them is incredible. And so I really want to thank you, not only as Sara, but also as an early career researcher, because I'm proud of being part of a journal and to a community that values excellence and visibility for the newest voices in the field. But of course, as most things in science, the job wasn't done alone. So I really want to thank my PhD supervisor, Professor Laura Penterici there, and not only for the work, of course, but for the best PhD one could ever imagine. And also all the co-authors, collaborators, friends for the infinite support. And also, last but not least, I want to thank you all, the scientific community, because meeting you at conferences like the EAS, thinking with you, asking questions, or sometimes daring to ask them, thinking together, helps a lot. So thank you so much, and thank you again.
It's hard to go after Sara. So now I would like to thank you also very much for winning for this award. And just simply also would like to give a very big thanks to my PhD advisors team, which led me to give me to this path to study edge-on disk, which is something that I really push forward in my career. Is something that is really at the center of my work now. And really, in particular, I want to thank this edge-on team, which has been looking for the edge-on disk and identified it with Spitzer, and then identified them with HST, and finally gave the first observation with ALMA that I was working on. So this is François Ménard, Carl Stapelfeld, and Gaspard Duchesne. I would really thank them for that. Yeah, and that's it. Thanks all for being here. Thank you.
Okay, just thank you very much, all of you. And then next year is your turn, please.